Alright guys, welcome back. The topic of today's lecture is going to be the logistic equation. So the logistic equation is really just an example of a sequence that models populations. So I'm going to say it's a sequence that models populations. So what exactly do I mean by that? So it's a sequence, right? We know a little bit about sequences now, but it models populations. So for instance, it might be something that tells us from one time to the next how the population of, I don't know, kangaroos in Canberra might grow or decline, right? Based on how much food is available, how much the kangaroos are reproducing, etc. Okay, so you could use it for lots of different populations of things. You could use it for people, you could use it for kangaroos, you could use it for koalas. You could use it for lots and lots and lots of different things. Okay, so enough talk. Let's actually define what the logistic equation is. So the logistic equation is exactly this. So as you might kind of expect, right? If it models populations, the population of something, right? It doesn't change hugely from one year to the next. So for instance, the population of say kangaroos in Canberra, right? That would the population next year you would expect to not be that far away from the population this year, and furthermore you would expect that it actually depends on the population this year. So tying that back to sequences, you might expect that the sequence would be generated by an iterative definition, right? That's just saying that the next term in the sequence depends on the previous term. So that would be right. So it has an iterative definition. So Tn plus 1 is equal to some number. So this a is just some number times Tn times 1 minus Tn. So we're not going to worry about this too much because we are in maths class and not in biology, for instance, or not in ecological science. This number is just some combined birth and death rate. And basically, the bigger it is, the more the population is growing. The smaller it is, the more likely it is to die out. Okay. So and it's just a number. So basically, we have some model to tell us what the way the population is going to change, and that model will have a particular value of a. So it's just a number. Okay, so let's do an example of generating a sequence from this logistic equation. So that example. So I'm going to give you a particular example. First of all, I have to tell you what a is. So a in this example is going to be 2. Now, if we're going to generate a sequence from this, we also have to tell you what the initial population was, right? So I'm going to call that T0. And I'm going to say that that initial population was 0.6. Now, that doesn't mean 0.6 of something, but it means 0.6 of a population. It's just a number. We don't really need to worry about it too much. So this is the initial population. Okay. So given that, let's go ahead and generate our sequence. So we had this one up here, right? So Tn plus 1, this is the one we're going to keep referring to. So Tn plus 1 is a times Tn minus times 1 minus Tn. So let's just write this out with a in there. So Tn plus 1, just erase that. Tn plus 1 is equal to, well, a here we said is 2, so is equal to 2 times Tn times 1 minus Tn. Okay, and we said that T0 is equal to 0.6. Now what I want to start with is calculating T1, right? Because we know T0, so when n is equal to 0, when n is equal to 0, this one here is Tn plus 0 is T0 plus 1 is T1, is equal to 2 times T0, so that's 2 times 0.6 times 1 minus t0 again is 0.6. Okay. So now, I know I always tell you guys that I like to do calculations in my head, but what I'm actually going to do is use a calculator for this one, because I'm feeling a little bit lazy today. So, t1, we said is 2 times 0.6, so 0.6 times, brackets, 1 minus 0.6. Ready? So that number is 0.48. 0.48. So now that's the n equals 0, or the t1 term. So now we'd like to find what t2 is. So we're going to look at n is equal to 1. So t2 is equal to 2 times, this number here would be t1, so that's the one we just calculated, so 2 times 0.48 times 1 minus t1, 0.48. Alright, so let's do this. So I'm just going to put this in memory so I don't have to retype it. So memory plus 2 times memory recall, so 0.48 times bracket 1 minus recall 0.48 is 0.4992. Okay, so T2 is 0.4992. So now let's work at the next term. 2 times 0.4992 times 1 minus 0.4992 is equal to, okay, let's work this out. So, oops, I think I just took that out of 2 times 0.4992 times 1 minus 0.4992 is 0.4999872. 0.49, or 4 nines, 872. Okay, so it looks to me, right, like we're getting really, really close to 0.5. So what I would say here is that I reckon you guys could actually try a few more terms, but you're just going to keep getting numbers closer and closer to 0.5, closer to a half, right? So this is an example of a particular kind of behavior of sequences, and it's called convergence. So convergence of a sequence means that basically as our sequence goes on and on, so as n gets larger, our sequence approaches some value. So Tn gets closer and closer to some number. Right? So let's say, let's talk about this example here. Okay, so we would say that as n approaches infinity, right? So that means n just keeps getting larger and larger and larger. We would say Tn approaches the number, right? Some number, 0.5. Okay. So as n approaches infinity, Tn approaches 0.5. So the way that you would read this is, as n approaches infinity, Tn approaches 0.5. Of course, not all convergent series converge to 0.5, but this is, I was just wanting to do one particular example, so it would converge to whatever it converged to. Okay, so that's one kind of behavior of a sequence, but there are also other possibilities as well. So not all sequences converge, right? You can imagine that if one possibility is for them to approach some number, another possibility is for a sequence to just keep getting larger and larger, or for it to keep getting smaller and smaller. And that behavior is called divergence. So divergent series means as n gets larger and larger, so as n approaches infinity, Tn, so our sequence, either also gets larger and larger, or Tn approaches negative infinity, right? So it keeps getting smaller and smaller. So that's what we mean by divergence. So what might be an example of a divergent series? Let's look at, for instance, well, that really simple example that we looked at in the last video, right? Tn is equal to n. So if Tn is equal to n, right, as n gets bigger and bigger and bigger, obviously Tn is always going to be equal to n. So as n approaches infinity, so as it gets bigger and bigger, right, Tn also approaches infinity. It gets bigger and bigger and exactly at the same rate. Okay, so that's convergence and divergence of a sequence. There's also one other possibility, which is called oscillating. So it's also possible for a sequence to not approach one value, but to approach a couple and to go back and forth between them. So this is, so as n approaches infinity, Tn oscillates, so that just means goes back and forth, right, between two or more values, right? So the values might be like +1 and -1, and the sequence might just keep getting, basically going back and forth between something really close to +1 and really close to -1, for instance. Okay, so these are really just to introduce you to, and we'll be coming back to these later when we talk about sequences and particular kinds of sequences and particular kinds of series. They'll be really important then. But for right now, all you really need to do is try to remember those definitions, and we'll come back to them at a later time. All right, that's all for this week. See you guys.